Hello students, welcome to our new session on control engineering for BE 7th semester mechanical engineering student. We are talking about the steady state operations. In the previous class we have studied about the steady state analysis for a given general block diagram for a control system and steady state characteristic equilibrium in a system. In this session we are going to solve some numericals related to steady state errors. So how we are going to solve these numericals and which type of approach we are going to follow to solve these numericals, and moreover some of the numericals related to this particular are being asked in the final exams also. Let's take an example. Here a unit feedback system has G of S equal to 40 S plus 2 whole divided by S plus 1 S plus 4. So for the given unit feedback system, we need to determine first type of a system, second all the error coefficients, and third error for a ramp input with the magnitude 4. So here firstly we need to find the type of system. Our error coefficients means the error values whatever we are going to get for the input, that is the steady state input. So what we are going to get, steady state error coefficients, that we are going to find out. Then for a given input with a magnitude of 4, what will be the error, that is for a ramp input with a magnitude of 4, what will be the error. Solution: we need to determine the type of a system for the arrangement in the G of S, H of S in a general form. So we have G of S, H of S equal to 40 S plus 2 whole divided by S plus 1 S plus 4. Here, as this is a unit feedback system, so the feedback will be unit, so G of H of S will be equal to 1. Hence we have to bring it into a generalized form. For that reason what we do here is we need to divide this S plus 2 by 2 and multiply it by 2. So when we divide this one by 2 whole and this one by 2 and multiply by 2, what we get? We get 40 into 2, and here divide by 2 it will be 1, and here S divided by 2 it will be 1 divided by 2, that will be 0.5 of S. Similarly, the denominator we have S plus 1 form, we can write it as 1 plus S form, and here also dividing S by 4 and 4 here divide by 4 and multiplying it by 4, what we get here is 4 bracket 1, because 4 get cancels 1 divided by 4 is 0.25 times of S. So we get here after simplification, that is 4 cancels, so it will be 10 multiplied by 2 it will be 20, and we get 1 plus 0.5 times of S whole divided by S 1 plus S 1 plus 0.25 times of S. When we compare this one with the generalized form, that is G of S, H of S equal to K times 1 plus tau 1 S or T1 S bracket 1 plus T2 of S so on till 1 plus Tm of s by s to the power n bracket 1 plus Ta of s bracket 1 plus Tb of s, so on till 1 plus Tn of s. Here s to the power n will be telling here n the type of a system and k is the constant or amplification gain k 20. So we are going to get, when we compare this equation, this right hand side with this generalized form, we get to know that k is equal to 20 and s to the power n, here the power to s is 1, so here n is equal to 1. Comparing this with the standard form where n is a type of a system, so here n is equal to 1, so the given system is type 1. If by suppose s was 2, then the given system would be called as 2. Here the system type is 1. So based on the power of s, we can tell the type of the system. Next, let's determine the error coefficient. We know that for a positional error constant, which we have already derived, we know that Kp equal to limit g of s h of s as s tends to 0. So from the given problem, we have g of s as 40, which we have for g of s into h of s, which we have already found out, that is as 20 bracket 1 plus 0.5 times of s whole divided by s 1 plus 4s bracket 1 plus 0.25 times of s. So as s tends to 0, when we substitute s is equal to 0, so this term is going to be equal to 0, hence we get the 0 term in the denominator. So 0 multiplying with all these terms, what it will be? It will be 0. So here we get 20, here also it will be 0. So 20 divided by 0, that will be giving you the positional error constant Kp is equal to infinity. So positional error constant value Kp for the given system is equal to infinity. Similarly, to determine the error coefficient, that is the other error coefficient, which is called as a velocity error constant, that is given as Kv is equal to limit s into, here keep it in mind, s into g of s into h of s as s tends to 0. So here we will be getting s multiplied by the g of s h of s term, that is 20 1 plus 0.5 times of s whole divided by s 1 plus 4s bracket 1 plus 0.25 times of s. Here before substituting s equal to 0 in this one, we will be simplifying this one. S gets cancelled. After cancelling s, we get 20 1 plus 0.5 times of s whole divided by 1 plus 4s 1 plus 0.25 times f. As s tends to 0 means nearing to 0, we can substitute the value of s here. So here s is equal to 0, this will be 0, s is equal to 0, this term will be 0, this will be 0, hence we will be ending with here. After substituting s is equal to 0, we will be getting 20 divided by 1, hence the velocity error constant Kv will be equal to 20. Next, to determine the error coefficient, that is acceleration error constant, that is given as k is equal to, here the formula is limit s square into g of s h of s as s tends to 0. So before substituting s tends to 0 or applying limit into this one, we'll simplify. So in the denominator we are having s, so this get cancels with this one, remains with s 1 plus 0.5 times of s into 20 whole divided by 1 plus 4s 1 plus 0.25 times of s. As s tends to 0, putting s is equal to 0, this will be 0, so it will be multiplying with this one, so all this whole element will be 0, so this one will be also 0, this is also 0, 0 divided by 1, it will be giving you a value equal to 0, hence the acceleration constant Ka will be equal to 0. Now we need to determine the steady state error for a given ramp input, and the value of amplitude or A is given as 4 from the data. Using this we have to find out the steady state error for the given ramp input. We know for a ramp input steady state error ESS for a function of t is given as A divided by Kb, which is a velocity constant. Hence we need to find out first Kb. Kb is equal to, just now we got it previously, velocity constant, that is limit s into g of s h of s as s tends to 0. The value was equal to 20, which we had found out second. Hence substituting in this equation 1, what we get? We get steady state error for a function of t equal to A divided by Kv. A is equal to 4 divided by 20. Hence steady state error is equal to 0.2. Means for the unit feedback system of a g of s h of s, when we are giving a input, that is a ramp input of a magnitude equal to 4, then the steady state error of this type of a system will be giving a value equal to 0.2. Let's solve one more example. Example 2. Here the control system is having a unit feedback. It has g of s equal to 20 by s 1 plus 4s bracket 1 plus s. Determine first different static error coefficients like what we had done in the previous problem. Here second part, what need to be determined is steady state error if input r of t, small r of t, equal to 2 plus 4t plus t square divided by 2. So this is the response which we are going to get from the input. This is the response input. Okay, so this one, when we are going to input into this control system, what will be the error or a steady state error from the given block, that is g of s, need to be determined. Solution. First we need to find out the static error coefficient, that is positional error constant Kp is equal to, we know that limit g of s h of s as s tends to 0. Here g of s is 20 divided by s 1 plus 4s bracket 1 plus s. H of s is equal to unit feedback, hence it will be by default 1. Okay, now here as s tends to 0, so substituting s is equal to 0, so we get here 20 divided by 0, 1 plus 4s 1 plus s, so it will be multiplied by 0, so 20 divided by 0, we will be getting Kp value is equal to infinity. This is positional error constant. Next we need to find out the velocity error constant. So we know that velocity error constant Kv is given as limit s into g of s h of s as s tends to 0. So we get limit s into 20 by s 1 plus 4s bracket 1 plus s. So here s and s get cancelled, then we substitute s is equal to 0. So here these values will be 0, 0 remains 20 divided by 1. So it will be the velocity error constant equal to 20. Next, similarly, we need to find out the acceleration error constant, that is given as k is equal to limit s square into g of s h of s. So we get here limit s square into 20 by s 1 plus 4 times of s bracket 1 plus of s. So here s and this s square get cancels, remains with s times of 20, s into 20. So putting s is equal to 0 into this one, so this one will be 0. So here this will be 0, 0. So it will be this is acceleration constant, Ka will be equal to 0. So we got the different constant, positional error constant equal to infinity, the velocity error constant equal to 20, and acceleration constant equal to 0. Next, we need to find or determine the steady state error if input, that is in a time domain, r of t equal to 2 plus 4t plus t square divided by 2. So before substituting or before putting this value, this has to be converted into from a time domain to a s domain. Hence for this we need to apply the Laplace transform. Applying Laplace transform on both sides, that is on a left hand side and a right hand side, what we get is r of s, that is Laplace transform of rt. So it is equal to r of s. Laplace transform of r of t, we have already discussed about this one, is equal to capital R of s. So this is r of s. Laplace transform of 2 is a constant, so it will be 1 by s. Laplace transform of 4, it will be a constant. Laplace transform of t will be equal to 1 divided by s square. So how we get this one? Here we can see Laplace transform. Here one table I have brought it. Laplace transform of f of t is capital F of s. Laplace transform of u of t is 1 divided by s. Laplace transform of c, constant, here it will be c divided by s. Hence here Laplace transform of 2 is 2 divided by s. Laplace transform of small t is 1 divided by s square. So this is 4 by s square. Now Laplace transform of here t to the power n. So t to the power n. Here we are having 1 by 2. So Laplace transform of t square divided by 2. This will be here 1 divided by 2 into here t to the power 2 it is. So it will be 2 factorial divided by s to the power n plus 1. Here n is 2. So n plus 1, that is 2 plus 1. N is 2. So this 2 factorial and this 2 factorial get cancels. So we will be getting 1 divided by s to the power 3. So hence the Laplace transform of t square divided by 2 is equal to 1 divided by s cube. Laplace transform of just t is, here just t is 1 divided by s square, so it is 4 divided by s square. Laplace transform of 2 is a constant 2, so it is C divided, like Laplace transform of C, it is C by S, so it is 2 by S. Next, we know that steady state error is given by ESS limit S into R of S by 1 plus G of S into H of S as S tends to 0. We know R of S equal to, from this one we can write this one as equation 1. Substituting 1 in this steady state error, that is equation 2. So we get here limit S in bracket, wherever R of S is there, we are going to replace it by 2 by S plus 4 divided by S square plus 1 divided by S cube. So you will be getting like this. Now here we are having 1 plus G of S into H of S. Therefore, wherever G of S, H of S is there, we substitute it by 20. This one we substitute here, that is G of S. Unit feedback system, hence it is HS will be equal to 1. We get, in place of G of S, we are going to bring this G block, 20 divided by S, 1 plus 4 times of S, 1 plus of S. Here when we take LCM of this one, this is going to come, substituting as S tends to 0. When we substitute in this one, S is equal to 0, we get steady state here error equal to infinity. So for the given type of input, that is RT is equal to 2 plus 4t plus t square divided by 2, steady state error is equal to infinity. This tells about the steady state error determination for the given type of problems. These are the typical types of problems asked on steady state error. So some more problems are solved in the notes. You can contact me at my contact address. I'll be sharing with you. Okay. Thank you.